Hey you guys, welcome back to another video. This is topic 2.6, competing function model validation. Throughout this course, we will have many opportunities to work with and create models based on a given data set. Three particularly important examples of this are linear, quadratic, and exponential models. Because these three types of models occur frequently in the real world, there is a heightened focus on them in AP Precalculus. On the AP exam, students will be expected to determine which model is most appropriate given a set of data. There are a few strategies and methods that we can use to determine whether a linear, quadratic, or exponential model is most appropriate for a given data set. So starting off with linear, we already know that, it looks like a straight line. It could have a positive slope or a negative slope. Now here's example of a table. So notice that the y values, they're not whole numbers. So that's why the graph looks like a scatter plot. So especially if it's a real world situation, you're not going to have a perfect line. So a lot of the points are not going to fall perfectly on the line. But if it makes a general shape of a line, then it would be considered a linear model. And you use a linear model when the data reveals a relatively constant rate of change. Okay, now the keyword here being relatively. Another word for relatively is roughly. That means it's not going to be perfect. And another word for constant rate of change would be roughly a constant first difference. Okay, so for example, if you look at the x values and then we look at the y values and see how they change. On the x side, you're adding 2 every time. And then on this side, you add 1.6. Over here, we're going to be adding 2.4. Here you add 1.4. And then here you add 2.3. So notice that the numbers are not exactly the same. So that's why the word roughly is important. Relatively or roughly a constant rate of change. These numbers are all somewhere around 1.5 and 2.5. So even though they're not the exact same or very, very close, they're a lot closer to each other than say, like 10 to 100. Those are really far apart, but these are not that far apart. So that's relatively a constant rate of change. Okay. Next up, we have quadratic. So we know that looks like a parabola. It could be facing up or it could be facing down, depending on what the leading coefficient is. And then here is an example table. And you use a quadratic model when the rates of change are increasing or decreasing at a relatively constant rate. So again, the keyword here being relatively. And then from one of the previous lessons, we learned that quadratic models have a constant second difference, but for real life data, we'll say it's roughly constant second difference. So it's not going to be perfect. And then the data generally follows a U-shaped pattern, or it could be an upside down frown, like I said. Okay. Next up, we have exponential. You use an exponential model when the output values are roughly proportional, and that just means that each successive output is approximately the result of repeated multiplication. And we talked about exponential growth versus exponential decay, so you can have both there. And then these, you can see, while the values on x are always adding 2, roughly the y values are changing by multiplying 2. Now it's not perfect, this is an approximation, but about, I'm gonna put the word about here just so you're not confused. So it's about times 2. Now notice that linear and exponential, they are both always increasing. So you have to be careful when you're just looking at the y values. So don't just assume that if they're always increasing, it's automatically linear, because exponential can also be always increasing. So you have to look at the rate of change versus the common ratio. So are the numbers adding relatively by the same number, or are they multiplying relatively by the same number? And that'll tell you whether it's one or the other. If you're just looking at the data, you can also make your own scatter plot and then kind of see how the points line up. So if it's a little bit more curvy versus perfectly straight, then that could be another giveaway. And then also if you are able to use a calculator. If it's a calculator active question, you can make your own scatter plot, and that way you don't have to make it by hand. So there's a few different options there. For exponential, I also want to add on here that a model is always exponential if the rate is given as a percentage. Okay, so a lot of the times they'll say, I opened savings account and the rate is increasing 10% every month. That's ridiculous. That wouldn't happen in real life. I wish it would, but it might be like 0.1%. But if it says something about a percentage, then it's automatically exponential. So the question does not have to say this scenario is modeled by an exponential function. If all they say is the rate is increasing at 10% or the rate is decreasing or depreciating at 17%, anything that has a percent is automatically going to be exponential. Okay, let's move on to example 1. Selected values from several functions are given in the tables below. Sketch the scatter plot for each table and then determine if a linear, quadratic, or exponential model is the most appropriate. So starting with table A, I'm going to plot my points. I have 0, 11, 2 and 8.2 would be around here, 4, 5, 6 and 2.3, and then 8 and -1 would be here. So I'm looking at this and this looks roughly linear. Again, it's not going to be super perfect. So notice that, I mean, most of my points fall on the line. This one and this one, they do not fall perfectly on the line, and that's okay because we're working with decimals. But this would best be modeled by a linear function. Okay, let's try letter B. We have -1 and +2, 1.5 and 5.5, 4 and 10.5, 6.5 and 5.75, 6.5, 5.75 would be around here, and then 9 and 2.25 might be somewhere around there. So I'm looking at this and it looks like it could be a parabola. Now I'm not going to hit all the points because it is, why can't I move this? There we go. So notice that the 2 on the inside, they don't quite touch, but this is the best fit line. There's no other function that would follow this curve like this, so this one has to be a quadratic model. Okay, and don't be worried about making sure you hit all the points. Some of my kids in class, they were trying to do this to connect all the points. If you do that, that would be an absolute value function, which is not one of the options, okay? So a V shape like this is for an absolute value, not a quadratic. So V's are for absolute value and the U shape is for a quadratic, okay? Now let's move on to letter C. We have 1, 10, 3, 5.2, 5 and 2.4, 7, 1.3, and 9, 0.7. Okay, so I'm looking at this and it does look a little curvy. It wouldn't make sense to make a straight line like this when I do see that it could be a little bit more curvy, like so. And I can see that this would best be modeled by an exponential function. And more specifically, this is exponential decay because it's decreasing. Okay, now let's try letter D. We have -2, +2, 1, 3, 4, 4.5, 7 and 6.75, and 10, 10.25 might be somewhere around here. Again, if you try to make this a straight line, you're missing a lot of the points. So instead of a linear, I think this would best be modeled by an exponential because you can see that it's a little bit more curvy than a straight line. Okay, and then more specifically, this would be exponential growth because it is increasing. They didn't ask to specify whether it was growth or decay, but it's a good refresher. Okay, moving on to residuals. We've covered this before, I think in lesson 1.13. When we create a model, we can use our model to predict values for the dependent variable, which is your output. And remember that your output are your y values. Okay, so you're predicting y values given an independent variable, which is the input, which are the x values. Okay, when using a model, it is important to remember that this is only a predicted value. So remember when you have real life data, like on these, you see how not all the points fall directly on the scatter plot. So the black line is your prediction. And then how far away you are from the solid black line, those are the actual values, okay? So the whole point of the residuals is that it tells you how far away you are from the actual value based on your prediction. So if we use the input values from a known data point to find a predicted output using our model, the difference between the actual output and our predicted output is called a residual. And the formula for the residual is the actual output value minus the predicted output value. And the actual output value always comes from the question. So it could be given to you on the table, if you're given a table, or if you're given a graph, or if you're given a word problem, it might be just typed out, okay? The predicted output value is from your calculator regression model. Okay, and then if you remember when you type your data into the spreadsheet, you can make calculations by typing F1 and then whatever the X value is in parentheses. Okay, so then remember that the formula is in alphabetical order, so A for actual comes first and then it's minus the predicted. So let's try example 2. The weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values for the weight W of t in kilograms of a particular newborn baby are given in the table above, where t represents the number of months since birth. Use the regression capabilities on your calculator to find a linear model of the form y equals a plus bx for the weight in kilograms of this particular baby x months after birth. Okay, so I'm going to highlight this because that's going to tell me exactly which setting to click in the calculator. Okay, so let me open up this calculator and then I'm going to insert a new spreadsheet. So listen spreadsheet. Next to A, I am going to type the letter X, and next to B, I'm going to type the letter Y. And then I'm going to type in my data. So we have 0, 1, 2, 3, 4. And then the weight at 0 months was 3.2, and then 4.2, and then 5.1, 5.8, and finally 6.4. Okay. Now I'm going to go to menu, statistics, stat calculations, and it told me to click linear regression of the form y equals a plus bx. So I'm going to click this one right here. And then on the X list, I am going to select X. On the Y list, I'm going to select Y, and I'm going to leave everything else alone, and I'm going to press OK. And then here I get the linear regression. I get the A and the B values. So I'm going to go back to my notes, and I'm going to write this. Now, even though the calculator gives you the variables X and Y, the variables here were W and T. So I'm going to write W of T is equal to 3.34 plus 0.8 T. Okay, and then just remember that normally on the AP exam, you need 3 or more decimals. If you click on the variables for A, you can see on the handheld identifiers at school, these decimals next to the F3 appear at the top. They usually appear at the bottom, okay? Oh no, what did I do? They usually appear at the bottom, but if you ever need more decimals, you can just click on that, and I completely messed it up. I don't know what happened. I wonder if I can delete this. Okay, there we go. But as you saw, there were no more decimals. Like that's it. So even though they require 3 decimals, if there are no 3 decimals, I mean, you could put 0 if you want. But if there aren't any more decimals, you don't have to put all of them. Okay. Letter B says use the model found in part A to predict the weight in kilograms of this baby 2.5 months after birth. Well, they told me in the question that T represents the number of months since birth, so I know that this has to be a value for T, so T is 2.5. I need to find W of 2.5. Okay, now for this easy equation, it would not be that much of a hassle to just type it out and plug in 2.5, but especially if you're rounding and you have a lot of decimals and you have a lot of variables, it's easier to use the trick where you just add a calculator sheet and then you type F1 using the keyboard at the bottom. And then once you type F1, it's going to make itself bold. And then now you can type parentheses, and they wanted me to find 2.5 months, and then you press enter. Okay, and that weight is 5.34 kilograms. Now this was a open-ended question, so I'm going to answer it with a sentence. So I'm going to say using the model found in part A, the predicted weight of this baby 2.5 months after birth is 5.34 kilograms. Okay. Just notice that I restated the entire question and I made sure to include units for both the input and the output value. So I made sure to say that it was in months and in kilograms. So make sure you're including your units as well. And also make sure that you're talking about both the input and the output value. So don't just say, oh, the weight is 5.34 kilograms. Like you need to be specific. When does that baby weigh 5.34 kilograms? And you would specify at 2.5 months. Okay, so make sure foolproof way is just to repeat the entire question, and that way you don't miss anything. Okay. Letter C says the actual weight of this baby 2.5 months after birth was 5.5 kilograms. What is the residual for this weight? Did our model underestimate or overestimate the weight of this baby? Okay, so for the residual, I know that it is the actual minus the predicted. Remember that the actual is given to you in the question, and it said the actual weight was 5.5 kilograms. So the actual weight was 5.5. My predicted weight was what I got in the calculator when I plugged in 2.5. So the predicted weight is 5.34. So to find the residual, I would just do 5.5 minus, and then the 5.34 that we had got earlier, and you get 0.16. Okay, so these are open-ended questions. So again, I'm going to repeat the question back to them. I'm going to say the residual for the weight of this baby 2.5 months after birth is 0.16. And you don't need to include units when you're talking about the residual. Okay, so what is the residual? The residual for the weight at 2.5 months after birth is 0.16. Notice that again, I included the input values because the residual changes depending on which value you plug in. So like just for example, like on this quadratic model, these values are going to have a smaller residual versus this one is going to have a way bigger residual. So that's why it's important that you specify what input you put, because the residual is not the same for the entire table. It is dependent on what X value you plug in, okay? And so that answers the first question. The follow-up question says, did the model underestimate or overestimate? I see that the predicted weight was 5.34, the actual weight was 5.5, and the actual weight was larger. So that means that the model underestimated the weight of this baby 2.5 months after birth because the predicted weight is less than the actual weight. Okay, all right. So like I just said, the residuals change depending on the X values that you plug in. Okay, now there is a way to see all of the points and how far away they are. That's called a residual plot, and you can use a residual plot to check the appropriateness of a model. So a residual plot shows all the residuals for a set of data and can be used to help determine if a model is appropriate for a given set of data. If a model for a given set of data is appropriate, the residual plot should appear without pattern. If you can see a clear pattern in a residual plot, then the model used for the regression was not appropriate. Okay, so the key takeaway here is if the model is appropriate, you will see no pattern. But if it's not appropriate, you will see a pattern. So just notice that they don't both say no together. So a lot of times some of the answer choices might say not appropriate because there is no pattern. So don't ever select that answer that's like a double negative. So it's either appropriate because there's no pattern, or it's not appropriate because there is a pattern. So it's not going to be not appropriate, no pattern. So don't select the answer choice that is a double negative, okay? Now, when you're looking at residuals, they might ask you questions about what regression they chose in the calculator. So I just want to show you that this is a 3-step process, and I'm going to show you the 3 steps. So we have the actual data that's given to you either graphically or on a table. And then we have the calculator regression, which is of course when you put the data into the calculator. And then finally, you can look at your residual plot. Okay, now I'm going to give you 2 examples. Now this table that we just did about the weight of the baby, they told me it was a linear model. And if I look at this, I mean the y values don't change by that much. We have +1, here we have, I can't really do mental math, but that's about +1, this is about +1, this is about, I'm just going to say they're all about +1, they're all approximately +1. They're not growing anything crazy. So from the actual data, I could have determined that it was a linear function. Now in the calculator, I selected linear because the question told me to use a linear model of this format. So when I selected linear on the calculator, I ran a linear regression. Now, if the data is linear and I select linear in the calculator, then I have done it correct. You want these two to match. If the data is linear, you need to select linear in the calculator. It would not make any sense for me to tell you that the data is linear and then you go and run an exponential regression in the calculator. That wouldn't make any sense. They have to match, okay? So for it to be appropriate, you have to select the type of data that you're given in the calculator. Okay, so if the data is linear and you run a linear regression in the calculator, then your model is appropriate. And if your model is appropriate, that means the residual plot will show no pattern. Okay, now let's say we have the same table with the weights of the baby, and I know it is a linear function. But let's say I'm putting the data into the calculator and my finger slips, and instead of clicking linear, by accident, I click quadratic. Now, a quadratic model will not be appropriate for a linear function, for a linear data type, because they don't match. Okay, so if the data is linear and I select quadratic, my model is not appropriate. Therefore, I will see a pattern in the residual plot, okay? Or for example, let's say example 3, let's say I give you a graph, and then let's say that the graph looks like this, okay? That is clearly an exponential graph. If the data is exponential, I should run an exponential regression. So if the graph is exponential and I click exponential in the calculator, then I have done it correctly. The model is appropriate, so I will see no pattern. Okay, so it doesn't matter what you run as long as what you're running fits the actual data that's given to you, either from the table or from a graph. Okay, so it doesn't matter how the information is presented to you as long as it matches. Okay. So on to the next page. This is what a residual plot looks like, and you'll know it's a residual because it always says residual on it. And where it says 0, this line right here, that means that your actual value is exactly equal to your predicted value. Okay, that means that your model was perfect. So for example, if I say the actual weight of the baby was 10 kilograms and the predicted weight was 10 kilograms, when I subtract 10 minus 10, I'm going to get 0. Okay, so that means that the actual was exactly equal to the predicted and your model was perfect. Now that's not going to happen often. Usually you'll have underestimations or overestimations, and the distance of how far away you are from the line of 0 would be your residual. Okay, so that's just how far away you are from the actual data. Example 3 says an exponential regression was used to model a data set. The residual plot for the exponential regression model is shown above. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? Okay, so the first thing I need to determine is, does the residual plot have a pattern? I'm looking at this, I don't see a clear pattern, and if you were to try to put this together, it would just look completely random. So I'm gonna say that this has no pattern. And that means that if there's no pattern, then that means whatever model they used was appropriate. So I'm going to look at my answer choices and I'm going to eliminate the answers that say that there is a pattern. So letter A says there is no pattern, so I'm going to keep that one. Letter B says it shows a pattern over here, so I'm going to eliminate that one. And then I'm also going to eliminate D because it says it shows a pattern. Okay, now I'm looking at A and B. It says the exponential model is not appropriate because there is no pattern. So remember I told you to never select the one that's a double negative. So here it's saying not appropriate, no pattern. It's never going to be the answer that has two no's. Okay, so here we have the correct answer, which is the letter C. The exponential model is appropriate because there is no pattern. Okay, let's move on to example 4. A group of AP Precalculus students used a set of data to create linear, quadratic, and exponential regression models. After creating the three models, the students created a residual plot for each model type, see above. Based on the three residual plots above, which model was most appropriate for the data? Give a reason for your answer based on the three residual plots above. Okay, so what these group of students did was they had one set of data. Let's say they had a table. They put those values from the table onto their calculator and they ran three different types of regressions. Okay, so the calculator does allow you to do that. So if I go back to my spreadsheet, right now I have a linear regression. So even though I know the table is linear and I did the correct model, which is linear, the calculator is not going to prevent you from running other types of regression models, even if it's not the best fit model for that data. For example, if I wanted to, I could also run a quadratic regression. Okay, and it's not going to tell me no, it's going to run the regression. Okay, and then let's say, oh, and I also think it might be exponential. So the calculator is not going to prevent you from selecting any of these options. So what these students did is they had one table and they ran three different regression models. So like I have here in column F, I ran a linear. In column I ran a quadratic. In column K, I ran an exponential. So even though quadratic and exponential is not the appropriate model because the question literally told me to run a linear model, okay? But the calculator is going to allow you to run as many as you want, even if they are incorrect, okay? So that's what these students did. They had one table, and on the same spreadsheet, they ran linear, quadratic, and exponential. And then from there, they're going to analyze the residual plots to determine which one is the correct model. Okay, so I'm looking at the linear, and I see it does kind of have a pattern because it looks like this. So this one has a pattern. So that means that a linear model was not appropriate. Okay, so when it looks more smooth or like a really smooth curve, like this, that's going to be a pattern. Okay, the quadratic regression, again, I can see this smooth curve like so. So the quadratic residual plot shows a pattern, therefore a quadratic model is not appropriate. And then finally, we have the exponential. This one doesn't show a pattern. You can see if I try to bring these together, it would just be completely random. So since this one has no pattern, that means the exponential regression was the most appropriate. Okay, so again, these two showed a pattern, so they are not appropriate. This one has no pattern, so it is appropriate. So you see how the question mark is right here. So I'm going to start answering my question by repeating that sentence back to them. So I'm going to say, based on the three residual plots above, the exponential regression model was most appropriate for this data. Okay, so we've answered up to there. Now the follow-up says give a reason based on the three residual plots above. So I'm going to say because the residual plot does not show a pattern. Okay, now you want to be specific and say because the residual plot does not show a pattern. Some of my students in class were trying to say because the graph does not show a pattern. You got to be way more specific than that. Like what graph, okay? Because is it the exponential graph, the scatter plot? Is it a graph that was given like a different graph? Like you need to be specific, okay? And don't say it, like it, does not show a graph. It does not show a pattern. The graph does not show a pattern. On the AP test, they're really looking for you to be detail oriented. So you need to be very specific about what you're talking about, okay? So I mentioned that the residual plot is what does not show a pattern, okay? All right, example 5. Mr. Garcia hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r in feet. Should Mr. Garcia use a linear, quadratic, or exponential model in this situation? Explain your reasoning. Okay. So remember that for linear models, the equation is y equals mx plus b. So it's anything where you have a constant starting point and then you're multiplying the slope, which is, whatever. It could be, let's say you're a waitress and you get paid a base rate every day of $50 plus, let's say every table that you help, you get an extra $10 per table, something like that. Or it could be pizza. Let's say you order a pizza and the cheese pizza is worth $5, and then every topping that you want on top of that is an extra $2. And then it depends how many toppings you want. Do you want one topping, two toppings, three toppings? So the price goes up based on a number of toppings. So it could be something like that. For quadratic, remember that for quadratic models is anything, absolutely anything that has to do with area. We talked about that in topic 1.13. And then exponential models, that's mainly going to be like population growth, the depreciation of a car, an interest account, something like that, or anything that has to do with a percentage. Okay. So we're talking about painting. Okay, so if you think about a big mural and then the number of paintings, and he's trying to paint all of these circles on the wall, you're going to first need to determine how big is the wall, how big are your circles going to be, and how, depending on how big those are, is going to depend on how much paint you need. So you're going to need to figure out the height, the width, the area of the circles. So this is basically like surface area. So anything that has to do with area is always going to be quadratic. So I'm going to say Mr. Garcia should use a quadratic model in this situation because the amount of paint depends on the area of each circle. Okay. Letter B says, after creating his model, Mr. Garcia uses it to purchase different special paint colors to use on his mural. In this situation, do you think it is more appropriate for the model to underestimate or overestimate the actual amount of paint needed? Give a reason for your answer. Well, when you're doing a painting, it would make more sense to have more paint than what you would need, because it would really suck if you're halfway through the painting and you run out of paint, then you have to go back to the store and you're going to come back, and that's just a hassle. So in this situation, it would be more appropriate for the model to overestimate. Okay, so I'm going to say in this situation, it is more appropriate for the model to overestimate the actual amount of paint needed so that Mr. Garcia doesn't run out of paint. Okay, and that is all for these notes. I hope that you learned something. If you have any questions, let me know in the comments below, and please subscribe to my channel. I will see you guys in the next video. Bye.